All right. Sorry. Okay, so my name is Paul. I work on Google. I work at Google. I work on CPU scheduler-related things. And I'm going to be talking about some work we've been looking at for threads and programming models in general. So obviously, the topic's a little controversial, so I'm going to go into some background first. When we say threading models, there's kind of three traditional models of thread you've seen over the years. The first is one-to-one, where every user thread has a back and corresponding kernel stack. This is actually currently pretty much ubiquitous. Everybody's doing this. This is what Linux does. This is what BSD does. This is what Solaris used to do. Windows does this. But there are some other ways of doing it. Previously, we saw N-to-1 and M-to-N. The second is really a variant of the first. In the first, what this means is you have multiple user-level stacks that are multiplexed onto one kernel stack. And the idea is you can perform user-level context switches without talking to the kernel. And this works, but if that thread blocks on the kernel stack, all of those user contexts are bound to it. So M-to-N was kind of a variant on this, which tried to introduce multiple kernel contexts. So you could do this in parallel. And this was originally popular for compute-driven workloads, where they believed the context switch time was really expensive. And so the more time they could spend in user space crunching compute, the better. And as we've shifted to more I/O-driven workloads, this is when you've seen more of a one-to-one threading model become prevalent, just because it's hard to coordinate those underlying kernel context exchanges in the N-to-1 and M-to-N approaches. So, OK, let's move aside a second to what we actually talk about. When people want to write parallel code, two really popular models are either you do a synchronous model, and you use a thread for every request coming in, or you do something like delegate events, and you have asynchronous worker objects, which are actually smaller than a thread. There's also message passing event loops, but really these end up typically being an implementation of the second. And when I say asynchronous and synchronous callbacks, I mean literally an asynchronous callback is a worker object where you dispatch some piece of execution, and this is normally handled by a thread pool, which picks up these asynchronous callbacks. Or you have a synchronous callback, which just looks like a method invocation. There's some complexity differences. So I'm going to preface this that we're interested in introducing a more synchronous programming model. And that's tricky for some of the reasons we'll discuss. But some of the motivation for that is the complexity that arises with an asynchronous model. And the complexity that arises with an asynchronous model is when you pass an asynchronous callback a view of an object, you're passing it a view, you're not passing it ownership. So in this trivial example where I have invoking function foo on x, or calling a callback on x, in the second case, I have to worry about the lifetime of x. I have to worry about synchronizing memory visibility of x. I have to worry about what happens when foo completes, what's the execution next. So this is, in 5 seconds, why we're interested in a more synchronous programming model from a user perspective. So pivoting back to where we were just now, callbacks are not actually a programming model, right? The challenge comes in that while threads are the base unit of concurrency you have for writing your application, if you're writing a server, they're not the currency of concurrency, so to speak, right? What you actually have are requests. And you have to have some mapping of requests onto threads. So this is where the two kind of programming models come in. The first is thread per request, which is really simple. Every time a request comes in, you start a new thread for that request. The programming model is really simple. Your execution is nice and linear. You write straight line code. Your data locality is good because your code proceeds exactly where it left off. The two things that kind of come up and why people start going to an asynchronous approach, despite the kind of complexity we've very briefly covered. Obviously, this is a short talk, so I'm trying to get through a lot of content fast. I'll be available after if you have specific questions. But the problem you quickly run into is that, first, your latency predictability now varies inversely with load. Right? If you have 1,000 requests arriving, but if you have 10 requests arriving, great. 10 threads run up, everything runs back, really goes really well. But suppose 1,000 requests arrive. Now you're creating 1,000 threads. You're coordinating 1,000 threads. And you run into all these things of, OK, well, which of these 1,000 threads is actually running? It becomes very difficult to predict the behavior of such a system. And your tail latencies invariably run into all sorts of birthday paradoxes where multiple threads end up on the same CPUs, right? You'll get good median latency, but very poor tail latency. So how people kind of patch this up is they move to that second approach, where you had these asynchronous worker objects. So you use, one other problem I should mention with thread per request is there's a second problem with suppose your request inherently contains some parallelism, right? If I make a request of a server, and that server wants to create threads to handle that request. Now you've got threads creating threads, and your problems just get, the suck increases. So they say, fine, I will take asynchronous callbacks. I will lose this nice straight line control. I will worry about all these ownership of my data objects, and I will make my concurrency slightly finer grained. So instead, I'll have these asynchronous callbacks that I can pass off to thread pools, and I can divide my requests into these little blocks, and I can chain them together to make up requests. And if I have concurrency within a request, I can create more callbacks. And you end up very quickly with lots and lots of callbacks on a fairly large pool of threads. So the nice thing is your latency predictability has improved. You can do more fine-grained management of these requests. You can start doing things to say, I know these requests are related for this request. You can achieve some lower overheads in that as you're switching between these requests, like when one asynchronous request finishes and the thread pool picks up another, there's no context switch, right? It's just dequeuing the next callback and executing it directly. Your code ends up having a lot of things like mutexes. You end up with a lot of fine-grained locking. You end up with a lot of things like notifications and conditions, where you have callbacks in threads conditionally waiting on something to complete because you've chained n of these callbacks together to actually make up your request. Suppose, for example, my request is going to fork two sub-requests to two servers, right? I'm going to do, for latency minimization, I'm going to take my request, and I'm going to duplicate it to two backends. So I have to create two callbacks and a third callback that runs when one of them is finished. So that's when you end up with these conditions synchronizing between them. So we were looking at all this, and we were looking at our servers, and we were looking at how to improve the programming model. And the kind of crux here is the way people have fixed thread per request is by actually introducing these concurrency objects that are smaller than a request. But we started out by saying a lot of the problems we had with thread per request were caused by this unbounded concurrency. And the communication between these thread objects is still really cumbersome. So we actually looked at, this dates all the way back to old research called CSP. Which basically introduced the idea if you have these concurrent executing processes and you have a nice way of communicating between them, you can have a fairly synchronous programming model. And Go had a fairly good take on this. They have Go routines, which are very lightweight threads. They have channels, which combine, when you pass data across a channel, the key thing is you're passing ownership of that data. So now you don't have to worry about those lifetime issues we had with the asynchronous callbacks. You have synchronous operations acting on objects they own. And then you have some other nice things like select, which lets you multiplex. Windows has something for this with wait for many. We don't have a good analog in Linux. So we looked at basically a bunch of commonly implemented server patterns and commonly implemented applications, and we wrote them in these various styles, thread per request, thread per object, Go's kind of CSP take. And we consistently liked basically the semantics of the result that came out of this synchronous model. We thought the code was simpler, shorter, and easier to understand. So, of course, this is the real world, so we don't go, oh, everyone should write their code in Go. We go, how do we make this work in C++, right? How do we bolt yet more features onto this beast? And so one of the real barriers to adoption comes back to that threading models we talked about at the start. One of the costs with a one-to-one threading model is it means that we have to switch both the kernel state and the user state every time a thread exchanges. We also have the kernel scheduler doesn't really know what user space is doing, so it often can't make the best decisions with coordinating those exchanges. So let's just first talk about the overhead this implies. So if we were to just take a pipe and two processes communicating across a pipe and time them context switching 1 million times, you'll actually see, and this is, for reference, this is on a 2-socket system. This is fairly representative of a modern server, 2-socket Intel, 12 cores a socket. And you'll actually see a fairly large variance. This obviously depends on certain scheduler operations and certain scheduler configurations. But this is not an unreasonable set of numbers to see. And OK, so well, that was a pipe. What if we actually use a futex, right? Because pipes introduce VFS. There's a bunch of extra locking they do. Futex is a fairly minimal way of doing it. 2 threads, same process, switching across a futex. So yes, we see some improvements. We get down to about 2.7 microseconds. But 2.7 microseconds is a really long time, right? If we're talking about doing these really fine-grained concurrency operations, and we're saying you should write your server as like 50 little threads, but you're going to have to pay like 3 microseconds every time you switch between one of these threads. This isn't going to fly, right? And this is kind of one of the traditional big barriers of adoption for C++ code. So where is this 2.7 micros coming from? So a big part of it is actually what happens when you have a wake-up CPU interaction. Because we're a fairly big fan of race to idle, when we get a wake-up, the thread waking up the other thread is normally still running, right? We don't have a synchronous, I'm waking this thread up and going to sleep operation. So what that means is the scheduler sees a wake-up, and it goes, oh, you're waking up another thread. And it sees, oh, you've got an idle CPU. So I'm going to locate that thread you just woke up on that idle CPU. Even if these two threads both correspond to the same request, and I'd really like them to run together because I've just put some information on the local cache for that CPU. So, OK, we send the IPI back over to the host CPU, and then our thread immediately goes to sleep. Great. And in this benchmark, we're coming back. So we saw these kind of 3 bandings in the result. You saw a banding around 1, you see a banding around 3, you see a banding around 6. These actually correspond to where your threads end up getting placed. If you happen to get really lucky and run on the same CPU or the hyperthread pair, you can get down to about 1 to 1.3 micros. If you're running on the same socket, you'll see 3, and if you're running cross-socket, you'll see 6. This was on this particular machine with these particular reasonably standard configurations. So if we can eliminate some of that variance, right? We can pin them to a single CPU. And we can use affinity. And this is one of those things that people end up doing these tunings in practice to get this thing, but it's really difficult to realize. It's hard to maintain the configuration. It's hard to keep it stable. And you also lose out on the load balancer, right? There's a lot of times where people have run a configuration where they hand-tune their application with lots of different pinnings. And we actually did this with web search. And then you take away the pinnings, and it suddenly runs faster. And it's like, and the reason for this is you got locality with the pinning, but you lost capacity, because when there was idle CPUs, you weren't able to realize them. So, OK, so if we go, OK, fine, go back for a few ticks, pin, we can get down to a microsecond. But we've kind of run up against a wall at this point, right? There's no cheaper operation for switching between these threads. And we've already pinned the affinity to the single CPU. This is the raw cost of the actual switch. So if you decompose that, there's 2 really interesting observations you can make. The actual ring switch into privileged execution, it used to be, when people were considering M2M models back at the start, what they were actually trying to escape was the cost of this privilege escalation. It used to be that getting into privileged mode on hardware was really expensive. The schedulers back then were very simple, right? These were uniprocessor machines, but the privilege switch was expensive. So the reason people were doing these hybrid models was to avoid the ring switch. It actually turns out now this has been inverted. Intel added, there's a funny backstory here. So we actually have Microsoft to thank for this. Intel went to Microsoft back in the 90s, and they said, what can we do for you? And Intel said, well, we'd really like it if you made the UD2 instruction faster. And they were like, why are you using UD2? And it turned out they were using that for their syscall interface, because it was actually faster than the int, software interrupt instruction. So they'd set up their call frame in UD2. And so Intel went, well, then luckily they went, well, this is a little retarded. We should add an instruction for this. And they added the sysenter, syscall. AMD and Intel both did a variant, and then they got merged. But with the 64-bit, I mean, this is 60, in long mode, which most servers are running these days, we had this really fast instruction for getting into and out of the kernel. And it actually turns out, if you use this, and the syscalls do use this, that you can do this round trip in under 50 nanoseconds on modern hardware. So what that actually means is that big cost we saw before wasn't the privilege. It was all the work we do for modern CPU scheduler. This has gotten much more complex, right? Machines have gotten much larger. We do group scheduling. We do fair scheduling. We do interesting load balancing. We do reference counting, because as the one thread unschedules and the next one schedules in, we're going to release a bunch of resources. What's that? What is making it slow? Oh, well, he's not making, he's making the context switch more expensive. He's not making the actual switch into the kernel mode. Oh, no, okay. Leave that aside for a second. There are always warts. So, OK. So we said, what if we take this information and put it together? And we added a new set of directed scheduling interfaces. And so it turns out with a set of 3 interfaces, one which is a wait, which enters a running thread into a synchronous wait state. One is a resume, which resumes a previously running thread. And one is a swap. And this swap is actually what we really don't have today. This swap says, I want to take a thread that's running and a thread that's in a synchronous state, and I want to exchange them, right? So what this then means is user space can have a larger pool of threads than the kernel sees. And it can have the notion of being runnable, which it tracks and maintains for these threads in user space. But the kernel only sees one of them, right? And it's whatever the user space is marked as runnable at the time. And when it wants to make modifications to this set, it can do the switch. And this switch is where we can get these really fast context switches. Because what we do is basically from the data of the kernel scheduler, that thread that was in the wait operation, right? It doesn't interfere with the kernel scheduler. It's in an interruptible blocked state. It looks just like a blocked thread. But because it's a blocked thread, it's not enqueued on any of the run queues. It doesn't have any scheduler-specific resources. So if we want to interpose their execution and run B instead of A on that CPU, we can put A at the same, without going too far into the scheduler specifics, but the scheduler maintains a per-thread virtual runtime. We can take B and put it exactly where A was, and put A where B was, right? We haven't lost any fairness. We haven't lost any time. And also, any objects A held references on, well, B is going to hold the same references. So instead of going over all those objects and atomically decrementing, and then going over all the same objects for B and atomically implementing, we can just say, well, B's inherited all these references, right? There's no need to do the dec and the inc. Just B's running now instead of A. A is where B was. There's a few other interesting considerations that you have to make with such an API. The first is that you actually want your waits and switches to be reversible. And what I mean by that is if I switch to something that's not waiting yet, you want it to queue. And the reason for this is because you had this, you've implemented some user scheduling on top of these primitives in user space where you're multiplexing your own threads and doing these fast switches between them. And suppose I mark a thread blocked, and I put it into a wait state, and some other thread wants to go, OK, I'm going to run that blocked thread and switch to it. You don't know that you didn't get really unlucky, and right after you marked it as blocked in user space, you got preempted and haven't actually issued that syscall yet, right? So by making them commutable, you make that case work much more nicely. We also didn't want any asynchronous user scheduling code. That's just classically terrible. And the third thing is really should have probably been the first is this has to be entirely cooperative with this kernel scheduler, right? There should be no special considerations. There have to be no special allowances. The kernel scheduler just sees these as threads. You can really look at this as basically the kernel scheduler sees a thread, which happens to be multiplexed onto a bunch of threads with these fine-grained operations. And it load balances this thread, which, again, happens to be multiplexed. And so user space gets to do this fine-grained sharing of the time that the kernel schedules it, right? It's saying, the user space has gone great. You've given me 8 milliseconds of CPU time. I'm going to multiplex between these 10 requests, these 10 threads, which happen to correspond to these 10 requests. So how fast can you actually get it going? It turns out pretty fast. So this is the unpinned case, but this is actually representative of what you'll see in a server, because in a server you typically don't pin because you want to get this natural ability to consume the capacity. So Google Mutex is our implementation of a mutex. We have our own internal one. But if you put them all side by side, running on an idle system, we can do these fast thread-to-thread switches in about 150 to 200 nanoseconds. As compared to the 2 to 6 microseconds of a regular context switch. And this is really kind of basically in the ballpark of a user-level switch. If you write this entirely in user space, you can get down to 20 to 100, right? But then you've got user-level threads. You've lost all the nice things that come with kernel threads, because there are some really nice things that come with it. You still have a one-to-one threading model, right? Any semantics existing in the previous applications that depended on having real threads, well, they still have real threads. TLS still works. Everything still has a unique TID. Debugging and profiling tools, right? GDB works, right? One of the biggest problems with the moment a language implements its own user-level threads, you try to debug or profile that language, nothing works, because GDB and pprof, they don't understand the stacks that language is set up internally. Well, these still have proper threads, right? You can kill them. You can use nice on them. It drops into existing code in a fairly compatible way. As long as you update your locking primitives, you can run codes with this fine-grained thread switching, and nothing too much changes. This is near the end, and I'm gonna add one other nice thing we can do with this trick. So obviously, before talked about, okay, so we can build an interesting scheduling API on top of these semantics. We can build interesting interfaces that look like Go's and run with performance similar to Go's, except they work in C++ and they work with real threads. A similar problem we can solve is socket locality, right? So suppose you actually have, so we just talked about receiving a request and doing all the work in all the work associated with what that request is asking the server to do. But it also turns out that in the client or in the server, suppose you're a root forwarding to leaf nodes, you also have to worry about making a request. And a lot of the networking libraries actually have this bi-thread implementation where your thread gets to make its request directly, right? It writes to a socket and says, I would like to ping this server. I want to request foo from server X. But because of the way the library is written, this response normally comes back to some network thread in that library. It doesn't directly come back to that thread that made the request, right? Because you may have many outstanding requests between many threads. So you've got some central library thread that's coordinating all the epols and handling the wake-ups. And you end up with the same problem that we had in the exchange before, where the networking thread now wants to wake up the client thread because it has work that it just received for the client thread. And it would really like the client thread to run where the networking thread's running. But it can't because, well, it has no way of telling the CPU scheduler this, because the moment you do this wake up, it's going to go, oh, I have a nice idle CPU over here, even though the soft interrupt and all the packet processing just happened on the CPU that the network thread's running on. So we can do some nice tricks here in that we can do a switch and invert the wake up so that basically temporarily block the network thread, switch to the CPU, switch to the thread running waiting for the response, and then re-wake up the network thread, meaning that you'll push the migration of the network thread instead of the request that just arrived. And so you can get natural locality without doing affinity, which is a pretty hard challenge for these kind of applications. This is really kind of what I was alluding to before, that context switching lacks the context we may be about to block, right? If we're waking up a thread because we've enqueued work to some producer-consumer queue for it, but then we block, we have no way of telling it we're going to wake it up and block, right? This synchronous switch operation is really implementing that. And then you can build a user scheduler and on top of that, which says, I have knowledge of these user-level threads, which are actually kernel-level threads. And when one of them blocks, we will translate that into either a switch into something else or a wait so that we can wake back up. And there's some nice, in closing points, there's some nice latency properties we can get from this. One of the biggest ones is when you're scheduling all these requests, the kernel scheduler doesn't have any knowledge of user space. So it has to do things like, well, this thread hasn't had much time recently, I'm going to run that. Which is why we get those kind of long tail latencies, right? We get this good median latency behavior, but this long tail latency. So because we have moved this coordination, because we've moved the coordination of which thread gets to run to user space in an efficient way, we can say, well, I actually want to run this thread because it's had the request that's been outstanding the longest. We can do things like FIFO by arrival order, even if those are in separate, even if we have 5 threads corresponding to that one RPC. So we've been able to observe some really nice tail latency effects on a server doing. So as an example, some of our identity servers, we have 150 microsecond average response with a 1,000 microsecond tail, as compared to something like we had a 40K microsecond tail when they were running with regular threads and we weren't scheduling the oldest thing first. So there was one other thing I wasn't going to mention, but I'm going to cover it very quickly because it actually interacts fairly interestingly with Frederick's presentation. So what I just covered was an API for doing directed scheduling. It actually turns out that if you build the full thing up, as we did, you end up wanting a second piece, right? You want managed concurrency, meaning if I'm running this pool of threads and one of them blocks unexpectedly, page fault, syscall, something else, I don't want to annotate that code. I don't want to poll that code. I want to be able to receive a notification in an efficient way that a thread running my user code has blocked, and I need to run another thread in its place. So we introduce, on top of the directed scheduling, a managed concurrency API, which lets you do that. Basically, you can have a group of threads, and that group can have delegates. And when a running thread blocks, what it does is it uses that directed scheduling operation to switch to its delegate. So we can now deliver notifications that a thread's blocked unexpectedly in a synchronous way without requiring POSIX signals or anything else. But we've also guaranteed that only one thread is ever running on that CPU. So we're always in a DynTIX state, in a DynTIX possible state when we're running in that application. So they can write threaded code using syscalls and everything else and still guarantee that only one thread is runnable. And similarly, we can do an interesting thing on the wake-up side, right? Suppose we have this managed concurrency and we have a delegate and we've said we want one thread running in this. These threads, you identify them into a context and you say, I want one of them running because I'm going to manage their scheduling. When a thread wakes up, what we do today, well, we wake up that thread, we enqueue it, and we do a preemption check. This is another source of latency for applications, right? If I'm processing a request and this thing comes in and arrives, the scheduler is going to run immediately, no matter what I was doing, and decide, well, should I preempt you? And do the work to do the wake up, even if it goes to another CPU. We can actually elide that even too. We can say, well, this is waking up into a group, and we've said we want one thing running into that group. You don't even get to wake up. Stay where you are. We'll schedule you later, right? And then we can just switch to them later when we choose to schedule them. So we can guarantee both when something blocks, we maintain control, and when something wakes up, we don't introduce overscheduling. It's worth covering, where previous approaches, activations, really fell down was this exact example, right? Activations was a 80s, 90s approach to doing managed concurrency with operating system support. And it was great for HPC, where you were running just compute. But there was the original activations paper, and then there were like 10 papers trying to fix the I/O model. Because what happens is every time activations gave you this way of declaring these user contexts and these kind of contexts and these ways of delivering events between them. But the problem happens when you wake back up one of your user contexts. You have to deliver to a running context this preemption notification, which has to include the previously running context, the woken context, and some meta context that encapsulates the two. So your wake-ups actually become much more expensive. With these delegates, we can actually achieve a much simpler trick. Because we know these delegates exist and they have a synchronous interface, we can say, OK, well, when the original thread blocks, say on a read or a page fault, we'll swap into the delegate. We're not actually losing any time at this point because we're waiting for that read to return anyway. And then the delegate can say, do I have any other threads to run? And it can consult its user-level list of threads, which, again, are kernel threads. And it can decide either A, I'm going to switch into one of them. And if it switches into one of them, well, we've maintained concurrency. Something else is running on that CPU. When that read returns, we won't actually deliver the preemption. It gets added to a list to that user space query when it finishes running that next thread. And we know it won't lose control, because if it ever blocks, it'll switch back to that delegate. And then, secondly, OK, well, suppose there was nothing else to do. There was nothing to run. Well, we can actually enter the delegate in a special state, which we call a basically wait for wake-up state, which says we're running in a context, but we have nothing to run. And there's a delegate available. And that means that when that original thread comes back from the read, resume it directly with no interaction with the delegate. Just pick the delegate up off this list of waiting delegates. Start the read thread running again with the delegate attached. And the next read thread, if another thread wakes up, it'll queue. You end up in the same situation. You're at capacity. But we didn't actually have to do any extra work there, right? We did read, block, switch to delegate. Delegate found nothing, waiting for the read to come back anyway. Block the delegate. Read returns. Read thread runs directly. Well, the delegate has to decide. If you want to do polling, you can do that in the delegate at that point in time, right? Because there's two things the delegate can do. It can say, there's three things the delegate can do. It can say, one, I'm going to switch to some other thread and become its delegate, right? Because basically, the delegates exist outside the context. Delegate can never be inside a context. So I'm going to switch to some other thread and become its delegate. That's one. Two, it can say, I have no other threads to run. I'm going to go block and wait for something to wake up. And the third is it can poll to see if the wake up has occurred, right? Because that wait for something to wake up is really this go into the special state where you atomically poll and switch to it immediately when it wakes up, right? And so there's an explicit asynchronous version of that where if you wanted to have your delegate wait for a while before it polled, then it could do a poll loop and then decide to enter that state. So you do have the option of implementing that policy, but we've tried very hard to make sure all of that is on the user space side. There's no kernel requirements for any of that. So yeah, so obviously this was dense for 25 minutes. I've covered a lot of things in a nutshell. I'm around if people have specific questions. I probably should take some quick questions now. What's that? I will be at the Scalability BOF. So, sure. Yeah. No, you still get to have multiple guys running. But how do you back up multiple guys in your model with the direct switch? Oh, no. You can only do a direct switch when you have, so that's why you have the asynchronous wake as well. So there's really two interesting cases, right? You can think of a CPU, like you have either num CPU, you have less than num CPU threads running, or more than num CPU threads running. In the less than num CPU threads running case, you're interested in introducing additional concurrency when things wake up, right? You might have this multi-wake up case you just described. And that's why we have the asynchronous resume operation, so that you can do that and recover that concurrency. But the moment you reach num CPUs, you never need to do an asynchronous resume because anything beyond that would be overscheduling, and you're really just doing multiplexing within that state. So when you do that multi-wake up in that case, all you're actually doing is adding them to some user run queue that a future scheduling operation will generate a switch to when it decides to run them instead. The syscall, I mean, it's all built on top of, like, it's built as a new set of syscalls. There are obviously, it has some integration with the scheduler, as you would expect. I don't think, the fundamental problem here is information, right? Trying to define a thick API where user space could transmit every piece of scheduling state it cared about to the kernel scheduler, it's incredibly thick. The whole intent here was that we can continue relying on existing load balancer, right? One of the key points was that we don't mess with the load balancer. The load balancer sees a thread running, and it has work associated with those threads. You can still use nice and everything else against those threads to rebalance them and change how the kernel sees them. And you don't have to do these affinity games. Because when you do this switch, we guarantee that what you switch to runs on the same CPU as you were running, assuming it wasn't a set affinity away from it. So we can you naturally get the load balance. You get the scheduler doing good things for you like time slicing, load balancing, but you get locality back. You get fine-grained concurrency. I can, yeah, we can definitely talk about it in the BOF. Yes.
Thanks, Paul. We have Tim, Dave, and Andy.